When it comes to measurement, there are qualitative measurements, which is like what kind of color it is and stuff, or is it a solid, is it a liquid? And those are really cool kind of things, all right? Qualitative analysis is actually an important part of chemistry, and we're going to do a whole series of labs at the end of Chem 223 if we have face-to-face labs, where we'll use qualitative observations to figure out what's in an unknown compound, stuff like that. But a lot of chemistry is quantitative, which means how much of something and what type of that you have. So if you're going to do quantitative measurements, which is a lot of chemistry, that's where the metric system comes in. But you can have different bases, and this is where the metric system is so cool. So for example, the base unit of length is the meter, the base unit of mass is gram or kilogram, depending on what you're talking about, base unit of time is seconds. You can apply the metric system to all of these. So let's use metric for the length part here. You can have a kilometer, which is 1,000 meters. You can also have a centimeter, which is 0.01 meters. You can apply all the different metric prefixes to these, which is really cool. And you can do the same for mass. You can do the same for time. It's really, really cool. However, there's a problem sometimes when you're taking measurements. You have to know about the accuracy and the precision of the measurements you're taking. And let's use this cheesy example here with a dartboard at a bar. And let's say that you have a couple, you're there to see your friends and you decide to play darts and you're really good at darts and man, you throw them and oh wow, all three of the darts right in the middle. Well, the blue circle represents the accuracy of the measurement. And you were super accurate. All right, they were all right there. And also because all three measurements were really close to each other, or all three darts were thrown at the same part of the board, you have a high level of precision. So accuracy and precision are both important in chemistry. Hopefully you have at the very least good precision, and of course if you're worth your weight and stuff, you should be able to make accurate measurements as well. However, same thing, you've had now a root beer or two, over 21 and stuff. Anyway, and you throw the darts again, but your root beer is just interacting so much with your body, you're too sugared out or whatever, that you throw the darts and oh, now they're not really close to that blue dot, but you threw them all in the consistent manner, and they all ended up in the same place. So I would call this a series of measurements that were very precise, like they all ended up about the same value, but they weren't very accurate. You wanted to be by the blue dot, and of course they weren't even close to that. So this is an example of a series of measurements which has high precision, but not very good accuracy. So your friends say, hey, don't worry about it. Here, have another root beer, and again, I'm coughing because maybe you have something other than root beer. Anyway, my silly jokes. Anyway, you have another couple of your root beers and you decide to try the darts once again. But this time you're pretty well jolted on caffeine, sugar, whatever the active ingredient is. And this time, you throw the darts and oh man, you can't hit the side of a barn. The darts are all over the place. They're not close together. You don't have good precision. The darts are all over the place. They weren't like tight together like they were before. And they're not even close to the blue dot. You don't have good accuracy either. Now I bring up this very silly example because this is what measurements are like in chemistry. You have to know, or you have to have an idea anyway, as to how accurate they are and how precise they are. And you should be, if you don't know anything about the chemical system, you hopefully will at the very least be able to have high precision, like you're paying attention, you're making good measurements that are repeatable. But even if they are close to each other and repeatable, you should be careful because you don't really know about the accuracy unless you have other methods to confirm what you think you know. Accuracy just refers to the proximity of the measurements to the true value, all right? So if you wanted a length of 3.5 meters and you measured 3.49, that's going to be pretty high. You can actually determine how accurate you are through what's called a percent error calculation, and we'll do some of this in lab if we have lab. Precision, on the other hand, refers to the proximity or reproducibility of several measurements to each other. So if your three darts are necessarily close to each other, that would be like making three measurements that are very consistent. They have very approximately the same values. And we can figure out how precise measurements are by using something called parts per thousand, which is a variation of what's called an average deviation. We will use percent error and parts per thousand in lab to tell how accurate and precise our measurements are. This is the thing, how to find experimental error or percent error, and I'm not going to go through a lot of details, but I want to just show here what some of the things are. In an average deviation, you'll take the difference between the average of your numbers and the individuals. Standard deviation is used a lot of times in math, although we don't use it in chemistry very much, and a parts per thousand is the average deviation divided by the average times 1,000 stuff, no big deal. This will make more sense in lab when we do it. But a parts per thousand, that's how we measure the precision, how close the measurements are to each other. Smaller parts per thousand means more precise, higher parts per thousand means less precise. Percent error, you do need to know the accepted value, maybe from an experimental paper that was published or some other important group. It's the difference between your value and the accepted value divided by the accepted value times 100%. And again, the smaller the percent error, the better your measurement, your calculation was. This is an example. You can go through it later if you'd like to. These are 4 boiling point measurements. They found the average of those 4 measurements. They then found the deviation, which is the difference between the average and the boiling point measurement. So for example, the first one, you would go 11.23 minus 11.19 for 0.04. For the second one, it's an absolute value, which means make it positive. So 11.09 minus 11.19 comes out to be negative 0.10, but it's listed as positive. Deviations are always absolute value, i.e. make them positive. Finally, if you take the average of all the deviations, you get what's called the average deviation. So if you took 0.04 plus 0.10 plus 0.08 plus 0.03 and hit enter, that would be some number, and you would divide it by 4, the number of deviations, number of trials, to get the average deviation. So the average deviation is 0.06. You could write that as 11.19 plus or minus 0.06 if you wanted. Parts per thousand, average deviation divided by average times 1,000. 0.06 divided by 11.19 times 1,000 is 5 parts per thousand, so they're pretty precise. And if the accepted value was 11.25, the percent error would be, again, the difference between them divided by the accepted value times 100. Percent error sometimes is absolute value, which means always positive. I put it here in the negative version just so you know what it's like and stuff. You should be good to go.